Hello everybody, this is Mika Seppälä. In this video I discuss the alternating series test to study series which are of the form summation k from 1 to the infinity negative 1 to the power k plus 1 times ak, where ak's are positive and form a decreasing sequence with the limit 0. It turns out that such alternating series always converge. The alternating harmonic series is the series summation k from 1 to the infinity negative 1 to the power k plus 1 divided by k. That is the sum 1 minus 1 half plus 1 third minus 1 fourth plus and so forth. The alternating harmonic series converges. In order to prove that the alternating harmonic series summation k from 1 to the infinity negative 1 to the power k plus 1 divided by k converges, we have to look at these partial sums Sm, where we take summation up to the index value m. We have to show that these partial sums form a converging sequence. In order to see why this is the case, let us compute first few values of this partial sum. Now first S1 is just 1, S2 is 1 minus 1 half, so that is 1 half, the yellow dot on the left. S3 is 5 over 6, the second red dot on the right. S4 is 7 over 12, and S5 is 47 over 60, S6 is 37 over 60, and then it continues. And it seems that the sums Sm, where m is odd, form a decreasing sequence, and the sums Sm, where m is even, form an increasing sequence. And this turns out to be the key to the proof of this result. So it seems that the red numbers S1, S3, S5 and so forth decrease, and that the yellow numbers S2, S4, S6 and so forth increase. Now let us take a closer look at this situation. Consider Em, that is the even sums, that is Em equals S at 2m, which is summation k from 1 to 2m, negative 1 to the power k plus 1 divided by k. Em plus 1 minus Em is summation k from 1 to 2 times m plus 2, negative 1 to the power k plus 1 divided by k minus summation k from 1 to 2m, negative 1 to the power k plus 1 divided by k. Almost all of these sums cancel, and we are left with only two terms, namely minus 1 divided by 2 times m plus 2 plus 1 divided by 2 times m plus 1. But 2 times m plus 1 is smaller than 2 times m plus 2. Therefore, minus 1 divided by 2 times m plus 2 plus 1 divided by 2 times m plus 1 is positive. So we conclude that Em plus 1 minus Em is positive for all m. This means that Em plus 1 is greater than Em for all m. The even partial sums for the alternating harmonic series, that is the sums Em, summation k from 1 to 2 times m, negative 1 to the power k plus 1 divided by k, form an increasing sequence. This sum Em is 1 minus 1 half plus 1 third minus and so forth, and the last three terms are minus 1 divided by 2 times m minus 2 plus 1 divided by 2 times m minus 1 minus 1 divided by 2 times m. We can group these terms. Negative 1 half plus 1 third is negative. And the next two terms also add up to a negative number, and so do all the other pairs of terms following this one. And the last pair is minus 1 divided by 2 times m minus 2 plus 1 divided by 2 times m minus 1. That is also negative clearly. And so the last term that remains is minus 1 divided by 2 times m, and that is also negative. So you conclude that Em is 1 followed by negative terms. So all these terms circled in red are negative. This means that all the partial sums em are less than 1 for all m. So now we know that the even partial sums for the alternating harmonic series, the sums em, form an increasing sequence which is bounded from the above by 1. And such an increasing sequence has a limit, call it e, and this limit is also less than 1. We have to consider also the odd partial sums of the alternating harmonic series. We call them OM. So OM is summation k from 1 to 2 times n plus 1, negative 1 to the power k plus 1 divided by k. The odd partial sums for the alternating harmonic series, sums OM, summation k from 1 to 2 times n plus 1, negative 1 to the power k plus 1 divided by k, form a decreasing sequence. To see that this is the case, consider OM plus 1 minus OM, that is summation k from 1 to 2 times n plus 3, negative 1 to the power k plus 1 divided by k, minus summation k from 1 to 2 times n plus 1, negative 1 to the power k plus 1 divided by k. This simplifies to 1 divided by 2 times n plus 3 minus 1 divided by 2 times n plus 2. 2 times n plus 3 is larger than 2 times n plus 2, therefore 1 divided by 2 times n plus 3 is smaller than 1 divided by 2 times n plus 2, and it follows that this difference is negative. So we conclude that OM plus 1 is less than OM for all m, so that the odd partial sums for the alternating harmonic series form a decreasing sequence. Now let us take a closer look at these odd partial sums. They are sums of the form 1 minus 1 half plus 1 third minus 1 fourth plus and so forth, and the last three terms are plus 1 divided by 2 times m minus 1, minus 1 divided by 2 times m, plus 1 divided by 2 times m plus 1. The first two terms, 1 minus 1 half, add up to a positive number, that is 1 half. So do 1 third minus 1 fourth, that adds up to a positive number, and so do all the other following pairs. The last one is 1 divided by 2 times m minus 1 minus 1 divided by 2 times m, that is certainly positive. And also the last term, 1 divided by 2 times m plus 1, is also positive. So all the terms are positive in this formula for OM, and this means that every OM is positive. So we have seen that the odd partial sums for the alternating harmonic series OM form a decreasing sequence of positive numbers. And such a decreasing sequence of numbers bounded from the below has a limit. We call this limit O, and we conclude that the limit of these odd partial sums, capital O, is positive. It remains to show that the limit of the odd partial sums for the alternating harmonic series and the limit of the even partial sums for the same series are the same. That is, that limit as m goes to the infinity OM equals limit as m goes to the infinity EM. To that end, let us consider the difference OM minus EM. That is summation k from 1 to 2 times n plus 1, negative 1 to the power k plus 1 divided by k, minus summation k from 1 to 2 times m, negative 1 to the power k plus 1 divided by k. Almost all terms cancel out in this difference, and we are left with 1 divided by 2 times n plus 1. So OM minus EM is 1 divided by 2 times n plus 1, and the limit of 1 divided by 2 times n plus 1 as m goes to the infinity is 0. So we conclude that the limit of the difference OM minus EM as m goes to the infinity is 0. And this means that the limit of the odd partial sums is the same as the limit of the even partial sums. That is, limit as m goes to the infinity, summation k from 1 to the 2 times n plus 1, negative 1 to the power k plus 1 divided by k equals limit as m goes to the infinity, summation k from 1 to 2 times m, negative 1 to the power k plus 1 divided by k. This means that the alternating harmonic series converges. In the proof that we just gave for the fact that the alternating harmonic series converges, we used only the facts that the numbers 1 over k appearing in the alternating harmonic series form a decreasing sequence of positive numbers and that the limit of these numbers is 0. This means that whenever we have positive numbers ak that form a decreasing sequence with the limit 0, then the corresponding alternating series summation k from 1 to the infinity negative 1 to the power k plus 1 times ak, that is a1 minus a2 plus a3 minus and so forth, that this also converges. The proof is precisely the same as the one that we gave for the alternating harmonic series. This is the alternating series test. The alternating series summation k from 1 to the infinity negative 1 to the power k plus 1 times ak converges if these numbers ak are positive, form a decreasing sequence, and if their limit is 0. Let us next estimate the error that we make when we approximate the sum of an alternating converging series by its finite partial sums. So we assume, as before, that ak's form a decreasing sequence of positive numbers whose limit is 0. Then the alternating series summation k from 1 to the infinity negative 1 to the power k plus 1 times ak converges. Let us denote the sum of this series by s. So s equals a1 minus a2 plus a3 minus and so forth. The finite partial sum Sm is summation k from 1 to m negative 1 to the power k plus 1 ak. And the difference of these two sums, s minus sm, is the infinite sum summation k from m plus 1 to the infinity of negative 1 to the power k plus 1 times ak. This sum starts negative 1 to the power n plus 2 times a n plus 1 plus negative 1 to the power n plus 3 times a n plus 2 plus and so forth. In this expression for s minus sm, we may take negative 1 to the power n plus 2 as a common factor, and the other factor is a n plus 1 minus a n plus 2 plus a n plus 3 minus and so forth. Now, we assumed that the ak's form a decreasing sequence, therefore each ak plus 1 minus ak plus 2 is greater than or equal to 0 for all k. And this means that also an plus 1 minus an plus 2 plus an plus 3 minus and so forth is greater than or equal to 0. But also we conclude for the same reason that negative an plus 2 plus an plus 3 minus an plus 4 plus and so forth is less than or equal to 0. So s minus sm is negative 1 to the power n plus 2 times a long sum, infinitely long sum, of which we can conclude that the sum is positive and less than a n plus 1. This means that the absolute value of s minus sm is less than or equal to a n plus 1. We have derived the following error estimate for the sum of a converging alternating series summation k from 1 to the infinity negative 1 to the power k plus 1 ak. Let us denote this sum by s. When we approximate that with the finite partial sum sm summation k from 1 to m negative 1 to the power k plus 1 ak, we make an error whose absolute value is at most the absolute value of the first term left out. That is, the absolute value of capital S minus capital Sm is at most a n plus 1. Let us use this error estimate to approximate the sum of the alternating harmonic series with error less than 1 over 100. In order to do that, by this error estimate, we need to compute 99 terms of this alternating harmonic series, because then the first term left out is 1 over 100, and the error that we make is then less than that. So S99 for the alternating harmonic series is 1 minus 1/2 plus 1/3 minus and so forth, and in the end plus 1 over 99. And this is approximately 0.698. We will later see that the actual value of the alternating harmonic series is natural logarithm of 2, which is approximately 0.6931. Hence, we did indeed get an approximation of the sum with error less than 1 over 100. To summarize, the alternating series test says that if AKs form a decreasing sequence of numbers with limit 0, then the alternating series summation k from 1 to the infinity negative 1 to the power k plus 1 times AK, that is the series A1 minus A2 plus A3 minus and so forth, converges. The alternating harmonic series is the most important example of a converging alternating series.